Hi, this week in Matrix. My name is Dan Callahan. You'll see me as Callahad in channel. I'm the engineering manager that supports the Synapse team here at Element. And joining me is Erik Johnston. Erik,
Hey everyone. So I'm a backend engineer on the backend team, and my job is basically to look after Synapse and try and make it go faster, and also make it stable, and add features and all that sort of stuff.
excellent. One of the things we've been saying in this week in Matrix quite frequently is that we've been working on memory performance and utilization in Synapse. And we wanted to take this opportunity, this Matrix Live, to talk a little bit about what takes memory in Synapse. Why is joining a large room, or is it just large rooms that are expensive? And what are we doing to try to kind of tamp that down and make it more consistent and reliable when you're self-hosting a home server? So I guess my question to you, Erik, is what does Synapse have to do when it joins a room initially? What even is a room, and why are some more expensive to join than others?
So a room is really just fundamentally a collection of events, and they form a nice graph. So when you send a new message, we send it as an event, and it just points at the old event, and there you go, and you send it off to all the users in the room and all the servers in the room. Great. The problem becomes because we're decentralized, we have no server that decides who's in the room, who's not. We have to encode all of that information into the actual graph itself. So that's why you see when people join the room, you have a membership event to say this person's joined or this person's left, etc. So all of that is encoded inside of this graph. Now, obviously that means to know who's in the room, you need to be able to fetch all of that from the graph. Fortunately, when a server joins a room for the first time, it doesn't need to get the full graph, but it does need to get enough of the state of the room, so all the joins, and there's another graph on top of that, so you make sure that you can get all of the necessary joins and leaves and that sort of thing. The problem with all of that is that because it's decentralized and servers come and go all the time, it's very hard to delete state, because if you just drop the state on the floor, another server comes along and go, oh, I have this piece of state, and then you might get old pieces of state creeping back in, and that would lead to people joining and leaving, and when they didn't actually mean to, which is sucky. So what we end up with the situation is that you just have the state that's encoded in the graph, which just grows and grows and grows and grows over time. So for each time someone joins the room, you get a new entry in that graph. This just means that for what we call large rooms, i.e. rooms with large amounts of state, i.e. lots of people have been in the room at some point, when you initially join, you have to just pull all of that data down to be able to understand what's going on in the room. So you don't need to get the whole graph on the whole history, but you do need to get all the state and all of those sort of events down, which can take quite a few megabytes, to put it mildly.
So you can, correct me if I'm wrong, but you can almost think of these events that are going to the room, which are both messages and then also changes to the state of the room. So the topic gets updated, or a person joins, or a person leaves, or someone's kicked, or someone's given a different power level. All of those are events that exist in this graph, almost like a get repo, where you have
Yep.
a bunch of different nodes that all kind of, they all have a parent node, and they all kind of form this graph, this tree structure. In Git, it's possible to do a shallow checkout where you say, actually, I only just want the latest. I don't want the whole history. Is there something like that we could do in Matrix, or do you really need to get all of the state events?
So in some ways, we already do a shallow thing in that we don't need the full history, and we just need to get down the state. And we have extra metadata on there to make sure you can authenticate those bits of state and things. So in some ways, we're already doing that. It's just for really large rooms, in the same way for really large repos, that's still quite a lot of data coming down. We can do things, especially for public rooms, where we try and be more selective about pruning some of that data. And so when you join a new room, so when a new user joins, it doesn't necessarily need to point to its old join event and things various small bits and pieces like that to really try and minimize what's coming down when you join. But fundamentally, what you end up is you still need kind of these one entry or one event per everyone that's ever been in the room. And you can dial that down slightly, but right now that is what you need. And especially for free node rooms where lots of people are coming and going, that can be a lot of people.
And so something I'm curious about is where does all this state come from? Because things are federated, the room can kind of almost exist somewhat independently of any given home server. That's in the same way that, sure, I have Synapse, you can get to it, github.com/matrix.org Synapse. I also have a copy on my laptop. And they share the same IDs and the same commit hashes. And so, does the repo really exist or really live in one place or another? Does the same thing kind of apply to matrix rooms, that if I'm a home server and I'm joining a room for the first time that has two other home servers in it, where do I get that graph from initially? How does that information flow in?
Yeah, I mean, the rooms can absolutely be independent of or be on different servers. And like because the internet is atrocious, right? Sometimes half the internet can't talk to the other half, and that's absolutely fine. Like this, but everyone in the room will still be able to talk so long as they can get to their servers. And then when the links come back up, what will happen is that they just send everything they've missed to each other, and the graph kind of self-heals. So what you'd end up with is almost like a fork. People talk on both forks, and then it gets merged in. So in some ways, when we talk about the state of the room or anything like that, what we're actually talking about is a state at a particular point in the graph. And so when you join a room, you do need to pick a server, and exactly how you pick a server depends. If you've been invited to the room, you tend to pick the server that you've been invited. If you're clicking on a link, often that link will have some candidate servers. So you can see the little via equals on the end of matrix.2 links. So that's what they're used for. If you're joining via room alias, what happens is you you contact the server in the alias and ask it, or what's the room ID, and please give me some candidate servers to join via. Usually you then join via whatever of the room alias server, because you've just talked to it, it's up, and likely that is the server that's got the best idea of what the room is. But yeah, I mean, basically, when you join a room, you need the room ID and a list of servers that are probably still in the room, hopefully, and then you just iterate over that. And then what happens is you ask that server to generate a join event for you, which you then sign, and then it adds it to the DAG, and then sends you the join event and the state of that join event. And then hopefully that will be enough for you to either send events, so you'll know who's in the server and who's in the room, at that point, because you have all the state. Or more likely, you'll just immediately take that join event and start back paginating and pulling in some of the most recent history to see what's been going on, if the history visibility allows that.
So you said the DAG, and that's just the directed acyclic graph, the tree structure of all these events. And so what happens is a room is a data structure that's shared. It's a big branching tree that's shared and replicated across a number of different home servers. Exactly. When you join, you go to one home server, you try to find one that has that room and say, give me a copy of all of the state that, for this point in time that I'm joining, which will tell me who has ever been in this room, who is still there, who joined and left, etc. And that's a separate set of queries, a separate set of information from what the messages have been in the room, the back pagination.
Yeah.
So joining a room sounds like that's going to be a pretty big operation. Is that the biggest operation in terms of memory use or resource use in general? Or are there, what else can really cause a server to bog down?
So joining a room is maybe not that bad in terms of CPU, but it's the biggest in terms of actual just memory usage, because you have to have everything in memory at one go.
Okay, and so what we've been focusing on the Synapse side is, at least for the last month or so, really focusing on memory. And that seems like the most expensive thing you can do memory-wise is join a room that's had a lot of state change, because you have to load all of that in memory at one time. Yeah. And so I imagine one way to attack that is to make the size of the things we're loading in memory smaller?
Sort of. So one of the things we've actually done is to change our parsing of the response to not load up all of the things into sort of native Python objects and then pass them into our event objects, because we previously done a lot of work to make our event objects small. So we do a lot of interning of strings and deduplication and that sort of thing. They're still a lot bigger. They're about, I think, 4 kilobytes for
Mm-hmm.
an average event, which is like 500 bytes serialized, just because Python has a lot of object overhead. But that is still significantly smaller than just the native dicts, because they will just be dicts, and every dict has like 100 byte or something overhead, and they're quite nested. And so by streaming parsing this, you don't have to load that entire body into native Python objects, which is a huge, like several times bigger than the end result of the events, because we do that deduplication of like the strings. So that's one of the things we've done. I did have a brief look at trying to make the events smaller, but then you really start to get into questions about how much you want to sacrifice memory for CPU speed. Like we could just have event objects be just store as the JSON string, and then every time you do an access, you just load the JSON string, take the thing out of the parsed format, return that, and then drop the parsed format. But that is obviously significantly slower than what we have today, but is like, it would save so much memory, like 10 times the amount of memory. So
Right. So in Synapse today, and Synapse up until today, what would happen when you join a room is you'd see this massive spike of memory, and then it would drop by about half, and then be kind of steady. And what's happening there, if I'm understanding correctly, is you create the join event. So you're saying, I want my server, I want to be in this room now. That server then sends you all the state, all of the history of those kind of state changes as a JSON, as a big JSON file.
yeah,
So that gets loaded into memory. Then we parse that into Python dictionaries, into big nested dictionaries. And because there's a lot of overhead there, that then, so you've got like, 1x the size of the thing, then you've got multiple
yeah,
x that as a parsed dictionary format. And then we go through each of those dictionaries and turn them into our own internal event class representation. And that
exactly.
can be smaller again, but you still have that big spike
Yeah,
in the middle.
and
Is
because
that right?
yes, exactly. And the perverse thing is you've got your you've got the raw string in memory, which isn't that big. It's like 100 meg or something for some large rooms. You then pass that into this huge JSON, like you parse it from JSON, and then it's this huge native Python object, which you then need to store in memory for the entire time while you pass them into the event objects. So you have all three in memory at once. And then you can drop the parsed objects. But at that point, hopefully Python will give that memory back. And if you're using gemmalloc, for example, it will generally. But because of memory fragmentation, it will stop using a lot of that memory, but it won't be able to give it all back. So you have this huge memory spike, and it will go down a bit, but it won't go down as much as you'd hope.
And so that's one of the things that we've been showing off in This Week in Matrix is that we have more or less eliminated that spike, or cut it in half at least.
Mm.
Where on a new home server, I think you had results of initially spiking to around 1.4 gigabytes of RAM when joining Matrix HQ. And then that would eventually fall down and kind of stabilize around 800, 900 meg.
Yeah.
And now in some of your experimental forks of Synapse, you've gotten that down to spiking at like 650 and stabilizing right around there.
Yeah.
One, what did you do to do that? And two, when can we expect that in a Synapse release?
So the first thing is that we did what I was just talking about of the streaming JSON response, and that that just means that entire spike of parts of that 1.4 gig spike disappears, because all of that was just the Python objects. And there's a PR for that, which I cannot remember whether it's merged or not, but I'm hopeful that it will get merged, either has already been merged or will be merged before 1.35 is cut. So that should hopefully land soon. And that will help a bunch. There's also some sneaky changes in there around actually performance just after you've joined the room, because we do a lot of things like you have to mainly around presence, to be honest, because it then figures out when you join a room, it figures out what new presence it needs to send to which new servers and things like that. And we were just doing it really naively, and we ended up, I think, doing something stupid like 16 million calls to check whether a given user ID was local or not, just because we ended up in this n squared monstrosity. So what you actually saw before I fixed that was memory spike, go down slightly, and then the presence would pull all the stuff back and do all sorts of n squared work, and so it'd go up even more for a bit, and then finally drop down, hopefully. All of that is now fixed, and those PRs are now merged. So you now it is just really just that sort of spike of initially joining and deserializing. So that so yeah, the presence rework has landed. The streaming passes stuff is well, it's just going through code review and should hopefully land very soon.
Okay, so to kind of step back and sum up, the most expensive thing you could do in Synapse memory-wise and Matrix memory-wise is join a room, because you have to go and get all that state. And Synapse right now, but not Synapse next month, takes all of that state, keeps it in memory. Then it also parses that as a bunch of Python dictionaries, keeps that in memory, and then it converts all of those to event objects, keeps those in memory, and when it's done with that, it can discard the other ones. And so that's why we're seeing this massive initial spike.
And of course, hilariously, if that parsing takes too long and it goes over enough GCs, we won't actually drop those parsed objects necessarily terribly quickly either if we're not careful. And so you actually do no longer use them, but they're not been dropped, and it's just like, oh, and then you don't even see that nice spike. You just see this slow, like, dribbling off after a while.
Oh, that's really interesting. That's because garbage collecting systems typically will have generational GCs are common, where you say, all right, I haven't gotten rid of this object, I haven't gotten rid of this object, I haven't gotten rid of this object. Well, I'll stop looking at it as often because I think it's probably going to stick around for a while. And that means that you're not going to free that memory back up, even though you no longer hold any references to it. That's fascinating. But we're addressing this first by incrementally parsing. So instead of creating all those Python dictionaries at once, we're just like reading enough out of the JSON response to create one of them, convert that to event, do the next, do the next. The next problem was that you would then see memory slowly creep back up as we did a bunch of presence work, which we found ways to make less expensive to calculate, like, are you a local user or not, et cetera. So now we don't spike as high, spike about half as high, and we don't creep up afterwards. And so all of these things are things that we're working on that should mean, I guess, that drive towards this eventual goal. The reason we're doing all of this is that it's okay for a Matrix home server to take a lot of memory if it's necessary, but we don't want memory to be fluctuating wildly. We don't want these massive spikes where, you know, normally you can have the server humming along just fine under a gig of RAM, but then you go and join the wrong room and suddenly you need 8 gigs of RAM or something really pathological. And there are two things driving. One, it's just nice to have predictability there. It's nice to have that. But the other thing is that Element operates Element's Matrix Services, a software as a service where we will host home servers for you. And one of the things that's really important in a sort of multi-tenancy environment, so in our case, we're running a whole lot of home servers, but also you can imagine someone that's running a home server alongside a lot of other services in a cluster, is that you want things to be relatively predictable and relatively well behaved. And so that's kind of the key driver, is we should be able to estimate and anticipate how much memory it takes to run Synapse, and it shouldn't go tromping all over other services that you might be sharing that same node with. Is that kind of right?
Yeah, I mean, it's kind of one of those things where, you know, especially a lot of people love running Synapse on relatively small devices as well, like just loading up a 2 gig VPS or even putting it on a Raspberry Pi and things like that. And for the most part, it will work. But then if one of your users decides to join Matrix HQ and that suddenly takes 2 gigabytes of RAM, you end up with it just being killed. And then the user, and they'll probably get restarted by whatever service monitoring you have, and the user might not even notice that it's disappeared. They'll notice the join doesn't work, so they'll hit rejoin, and then that will just keep happening. So you like it, kind of, we're just wanting to get it so that kind of almost no matter what you do, hopefully you don't have huge spikes. We're trying to just smooth it out a bit, or just lower those spikes so that you just you don't have that sudden we have tripled our memory usage. And that's both for EMS style things, but also just people running on smaller pieces of hardware.
So I have one last question, which is something I've seen is that we have room versions as things change around, like the state resolution algorithm, as we make changes to that, or as we add features to change kind of the semantics of how rooms work. If joining a room, if the expensive part memory-wise of joining a room is getting all of the state and loading that into memory and parsing it, when a room upgrades from one version to another, we set kind of a tombstone event saying like, this room is done, the new room address is over here, and it effectively creates a new room. Does that effectively reset the amount of state that you have to pull in and kind of almost acts like a GC of past state events?
Yes, I mean, it absolutely does. So one of the ideas has been to just set up periodic, almost tombstoning, either doing it in the same way we do a room upgrade, or just having kind of almost epochs of the room where you can say, actually, this is a new epoch, and this is all the state that we've dropped. Because like the vast majority of the state is, to be honest, pointless. It's just leave events, which no one cares about. The only time you care about it is if you get some old bit of state to say that user was joined. You need to have something that says, no, they did actually leave. Otherwise, the user may accidentally get rejoined without meaning to. So yeah, I mean, so upgrading room is a great example of actually just bringing that complexity down. It will start to increase again, and when everyone rejoins, it will get large, but at least you've gotten rid of all of that, all those leave events. The reason not to do that is simply because, if servers are down and things like that, it can actually get quite tricky to make sure that everyone's aware of the new epochs and everyone's aware of the new tombstone. What you'll still occasionally see is people talking to the old room after some things have upgraded, which is a bit awkward. Normally, they'll quickly then get the tombstone event and then say, oh, the room has actually upgraded. But in that period where they've talked for those few minutes or whatever, no one would have seen that. So it is kind of, it's not seamless. That kind of thing is not seamless enough that we want to do it just automatically and regularly. There's an argument that we should make it that seamless, absolutely, but right now it's not quite there, and that's where a lot of the complication lies.
Thank you so much. I think that's a pretty comprehensive overview of what we've been doing, why we've been doing it, how things work under the hood. Long story short, if you've stuck with us thus far, or if you just skip to the end, memory spikes in Synapse will be getting way less severe soon. Ideally, by this time next month, you should have a much better experience.
Touch wood.
Yeah, touch wood. Something in here is made out of wood. I guess from all of us over here on Matrix Live Land, to all of you viewers, thank you so much, and we'll see you next week.
Yeah.
Bye.